Okay, so we're going to be looking at static particles today. This is now in the year 13 applied book. So that's the stats and mechanics book. Before, when we were looking at vectors, that was in the pure year 13 book, because vectors are in some sense a very, how can I put it? Vectors are applicable to many different areas in maths and in fact outside maths. So therefore they're not specifically unique to mechanics, even though they are used a lot in mechanics. However, the topics we're now going to look at are mechanics specific topics, so physics, engineering kind of topics. What we're going to look at today is static particles, sort of the exciting world of things that don't move. So let's just clarify what that means exactly. So the topic of static particles, forgive me if it's patronizing, but let's just confirm that we understand what we're talking about here. By static, we're talking things that don't move, at least within this context of considering physical objects in mechanics and how they move. A static scenario is one in which things aren't moving. And then particle, also a technical term, where we're modeling objects as points. So as in single dots, so it doesn't have any physical, it doesn't have any expression of its physical shape or size. It's just a single dot on a piece of paper, and that's how we're modeling it. We're choosing to model it that way for simplicity's sake. Obviously, at higher levels of mechanics, you'll start to undo that modeling of only choosing a particle, and you might be able to pick more complex shapes. But to start with the basics, we're looking at points. Okay, so then, and further thing I just want to talk about before we start looking at some examples of static particles and how we calculate the forces involved, is this important idea of being able to split up a vector into two components, and to be able to do it with respect to any axis that you choose. So I'm talking about like the XY axis is a sort of default pair of axes, and you can pick any one you like. So I'm just going to sort of try to illustrate this a little bit as best as I can. So maybe let's let me think how to do this. Maybe I'll make a table out of it. Okay, so I'm going to draw a few examples of vectors. Let's try and make them a little bit different if I can. Let's just do two. I don't need to overkill it, I think. Okay, and then what I'm going to do is, let me just set up the table first. Okay, what I'm going to do is I'll pick an axis up here. Let's say my axes look like this. Okay, they do need to be perpendicular. So this is the standard one, right? This is your sort of standard XY axis. And then what I'm going to do is, for each of these vectors, I'm going to split them into two components. I've drawn them on a flat piece of paper. They're two-dimensional vectors, so I can split them into two components alongside the two axes, the X and the Y axis. So in this case, if I were to do that, then my two components would be, let's draw it for the first one, would be this going horizontally and this one going vertically. Okay, this is nothing necessarily new. And this is the horizontal component, and this is the vertical component. Okay. Now I've used the words horizontal and vertical, but I've only used those words because they correspond to this axis that I've chosen, this horizontal and vertical X and Y axis. However, you can technically split up a vector any way you choose along any set of perpendicular axes. So let's just make sure we understand this concept. I'm going to just pick at sort of random another axis. So I'm just going to tilt basically the XY axis by some amount. Let's say this one, for example. Okay. Now remember, it is important that you've still got a 90-degree angle. Okay. In your axis, it's got to be 90 degrees. And then let's just see geometrically, not doing any calculations. You know, what does this actually look like? Okay, so in the first case, that one's a bit tricky actually. So I'm starting at the base of the vector here, and I need to go off in the direction which is parallel to that line, right? That's kind of, it's almost like my horizontal direction, and this is my vertical direction, or component, I should say. Right, so let's see if we can do that. So roughly speaking, it's quite narrow actually, be like that. And then I've got a tiny bit coming up. Oops, but I've got to make sure it's still perpendicular to the other one. Okay, so it'd be something like this. Right, that one's a little bit difficult in terms of illustrating it. Let's take a look at the second one. So that one we've got, so roughly speaking, it'll look like this, and then we've got the vertical one, you know, this component here. Okay, we split it sort of that way, right? So they're quite narrow, those ones. Let's pick another axis and then we'll get one more example. So let's pick another one at random. Let's choose, I don't know, this. Oh, let's just go a little bit more interesting. Let's sort of try and do that. That's too similar, isn't it? How interesting can I make it? Okay, I've gone for a straight up sort of 45-degree tilt of the standard coordinate axis. Let's see what we end up at. So we've got our two original vectors, and let's try and split them according to that. In this case, so remember, we've got to start at the beginning of the vector, and then just in any order, it doesn't particularly matter, we could follow the two axis lines. I'm going to follow this line first, that direction. So I'm going to be going sort of that way, and then down here. Okay. Remember, there's always two ways you can do this. You could also have gone that way, and then that way. Right, there's always two possibilities. It's the same with the others. For example, in the very first case, this one, we could say, well, you can go that way, and then you can go that way. Those are your two possibilities. It's still the same two components, isn't it? They're just in a different order. In fact, for the sake of completeness, it's probably a good idea to make that clear on all the diagrams. Okay, so you've got a choice. It's also a good thing to remember. You've got a choice which direction your components go, which order you apply your components. Right, last one. Let's see if we can finish this off. So I'm going to be going, let's say, this direction first, and then that way, or likewise, I could go that way. And remember, they're parallel, even though I haven't drawn it that way, and then to the right. Okay, that's my sort of best attempt. Hopefully that makes sense. And then the idea is, in theory, let's see if this works. If I drag the coordinate axes to the position where the components lie, it should make sense. They sort of lie along it. So those two green lines line up with the yellow ones, right? It just means I've drawn it correctly. Likewise here. Yeah? I should be putting it at the base of the vector. Okay. With the others, it mathematically speaking, it should line up. If it doesn't, it just means I didn't quite draw it right. But let's take a look. Right, so you see, you know, quite happy with myself there. So it quite lines up, yeah? But that's the point. That's what I was at least attempting to do. Yeah, similarly here, the green line lines up with the yellow line. So that's the sense in which I was using the axis as a reference point to guide how I decided to split up the vector. And then in this case, yeah, just about right, isn't it? The green lines line up with the yellow lines. Okay. So that's the concept that we want to try and get here. Okay. So obviously by default, if you're splitting up a vector into components, by default just go with horizontal and vertical, the standard XY axis. However, there will be scenarios, and obviously they're coming up in a moment, where it's useful to pick a different, I suppose you could almost call it, no, I don't want to use technical language that I'm not entirely familiar with. We'll just call it a rotated axis, okay? You can use a different pair of axes to split up your vectors, and mathematically all the results we hold about how vectors work and the relationships between them, they still hold. You're just using a different reference system. Okay, cool. All right, hopefully that made sense. And let's take a look at the next slide. Okay, resolving forces for static particles. So, bit of refresher. A static particle tells me the particle is not moving. Let's just be a bit pedantic and just follow the full line of logic here. The particle is not moving. Therefore, if it's not moving, it has zero acceleration. Okay. Remember, a particle can move and still have zero acceleration. That is possible, but as long as it's constant velocity. But if it's not moving, it's got a constant speed. And the speed is zero. It has zero acceleration. The speed is not changing, and zero acceleration by F equals ma. Resultant force is zero. Okay, so static particles have a resultant force of zero. And therefore, if we resolve all the forces on a static particle, we should get the number zero. Remember that resolving forces, what that really means is that's the best way I can it basically means add up the force vectors. I don't want to be too simplistic. Let me just make sure this covers all bases. Let's say add up the forces along a given axis. Oops. Or let's say let's not say along. Let's be a little bit more specific. Add up the force vectors with respect to a given axis. Let's say we're going axis. Okay. So you're adding up these force vectors and you're doing it with respect to a given axis. So if you get zero, that means the particle's not moving. And if I could just bring in the sort of thing we were talking about with those rotated axes, I'm going to just try and attempt to illustrate something. Hopefully this will make sense. So first off, let me just draw. I'm going to draw an object with three forces acting on it. I'm gonna cheat a bit and reverse engineer the situation. By which I mean I'm going to actually just draw my forces first, and I'm going to draw them so that they form a triangle. Okay. Let's make it a bit more of an interesting triangle. Okay, so they're making a triangle. And then what I'm going to do is I'm going to draw my object, whatever that may be, a little ball. So there's a little ball floating out in space, and it's got these three forces acting on it. So if they're acting on this ball, then obviously they're acting, from the ball itself. Okay. So from the way I drew those three vectors, you know that object's not going to move, because what happens if I were to add up these three vectors, put them head to tail? That's what adding up vectors is, remember, geometrically. If I gave you specific values for these three vectors and you added them up, you would get 0, 0 as your resultant force. And you know that because geometrically they add up to end up where they started. So this is a static particle right here, this yellow object. Now what's interesting is, again, if you had picked various reference frames, you'll still get the same result. So let's try it with the standard XY axis. Okay, this is the more obvious one. So if I now draw and split this all up, so we've got let's split up that one there. Oh, actually, I'm going to use yellow lines. I'm not going to do the dashed lines because it's going to make it harder for me to shift them about. So I've got that line there, that one there. I have to be a little bit approximate. So that one, okay, that one. Okay, so I'm splitting it up into vertical, horizontal. Let's say this way. And this way. Okay. And now let's see what happens if I resolve. And now let's resolve them separately. Let's resolve the horizontal and resolve the vertical. So if I resolve horizontally, can I do it without getting a chunk of that red? Okay, so I'm resolving horizontally. I'm taking all my horizontal vectors. And now look, the ones that are going to the right, okay, the ones that are going to the right, compare that to the ones going left. Same length, right? It makes sense. So let's write it now formally. Resultant force horizontally is 0. Okay. And looking at the vertical case, that one's going up. Let's do it over here. Then if I add that one going down and add that one going down, that's just because I haven't quite drawn it perfectly, but they would be the same length, right? And again, resultant force vertically is 0. Okay, so that should make some intuitive sense that that would work. So this is what I mean by resolving vertically and resolving horizontally. It means taking either the horizontal or vertical components of all the forces and adding them up. And in this case, we get 0. Here, remember, I haven't done any actual numerical calculation. So when I say adding up vectors, geometrically, that just means putting them head to tail. It still gives you the same result. Right, and now just one more try, but this time, let's use a different axis. So I'm going to just arbitrarily draw one, rotate it a bit. Okay, let's see what happens. Hopefully you have some idea of what might happen already. So let's try and approximate this as best I can and not mess it up. Sort of tilting my head as I look at the screen. So splitting up that one. Then this one here will be, oh dear, can I do it? There and down here. Okay. This one will be, let me do the long one first. Something like that, roughly. Arrowhead is there. And this way. Okay, I've attempted it. Let me just compare the axis. It's about right, yeah? Yeah, roughly speaking, it lines up. So let's see what happens. Let's take all of the ones in, we can still call it X and Y if we want to, just to make it easier to know what I'm talking about. Let's take all the X axis forces. So let me try and grab this one here. And that one there. Okay. And then let's add on to that the one going in the other direction. beautiful. Just almost. They should obviously be parallel, but you know. Okay, so there we go. Those forces along that x-axis cancelled out to 0, and likewise, is this going to work? There we go. Roughly speaking, as good as you can get using a tablet on a computer. There we go. Okay, resultant force is 0 along the x-axis and y-axis once again. Okay, so this is a really useful tool, really useful. We can pick axes however we like. There's nothing special about horizontal and vertical, right? And it almost makes sense because, you know, as human beings on this earth, we define horizontal and vertical with respect to the direction of gravity, which happens to be with respect to wherever you are on the earth, right? If you go to somewhere else on the planet, your horizontal and vertical are going to be different directions, right? Horizontal does not mean the same thing for me as it does for someone in, say, I don't know, in India it'll be a certain number of degrees shifted, won't it? If you go over to America, it'll be shifted in the other direction. It's respect to gravity. So it makes sense that there's nothing special about horizontal and vertical. Forces, they add up and they multiply with respect to any possible axis. The calculation ends up being the same. Right, so let's look at an actual example. Here we've got what we've got 3 forces, 2 unknown, particles in equilibrium, and we're going to resolve horizontally and vertically. So at the moment it's easier. We're just using horizontal and vertical. And we're going to find the magnitudes of P and Q. So I'm just going to draw directly on the diagram. If I resolve all of these forces here, okay, so that's the one on the left. This is my P that I'm resolving into 2 components. Q, I don't need to resolve into 2 components because it consists entirely of 1 vertical component and the horizontal component is 0. Okay. Now let's label the magnitudes of each of these. So you're going to need to use a bit of trigonometry. So this one here, this one is going to be 4 times cos 45, or sorry, sine 45. That's 4 cos 45. This force over here is 4 cos 30. That one's 4 sine 30. Oh, sorry, not 4. We're now talking about P, aren't we? So we need to multiply P, the hypotenuse. So remember, P is the length of the vector, sine 30, and here is just Q. Right. So now let's resolve vertically, and in fact let's just use the mathematical shorthand. So drawing a vertical arrow, resolve vertically, we get this one going up, this one going up, the P sine 30, and the Q going down. So it tells me that 4 sine 45 plus P sine 30 minus Q equals 0. And if I resolve horizontally, we're going to get P cos 30 minus 4 cos 45, and that equals 0. Okay, and the rest is just simultaneous equations, really. You do hopefully know what sine 30 and sine 45 are, and cos 30 and cos 45 are as actual values. So remember, sine 45 and cos 45, they're exactly the same thing, 1 over root 2. Sometimes people call this root 2 over 2. It's actually the same value. Sine 30 and cos 30. So sine 30 is a half, and cos 30 is root 3 over 2. Okay, these are sort of standard results. And then you've just got a simultaneous equation, which you can solve. I'm conscious that I've spoken a bit too much in the earlier section, so I'll just let you finish that off, or just trust me on the answer. If you were to solve that simultaneously, if you did it the nice way and kept all the surds, you'd get 4 root 6 over 3. And in the case of Q, you'd get 2 times root 6 plus 3 root 2 over 2. Okay. So the last bit of working I haven't done, which is just solve the simultaneous equations, you get these values. Okay. But the setup we've completely done. We've done the resolution of vertical and horizontal components. There is technically another way you could do this question, which is quite interesting. You could have used the trick whereby you've effectively got a force triangle. So what I mean by that is that you can, take the forces. So if I just try, let's see if this works. I'm just going to draw the forces on the diagram. Okay. Oh. I'm struggling to draw them on there. Let's maybe just duplicate the image slightly. So we've got that as our vertical down. We've got this one going up like that at about 30 degrees, and we've got this one sort of going up like this at 45 degrees, roughly speaking. And if you arrange that into a triangle where you're doing everything head to tail, then it's a static particle, so it should line up. Okay, it doesn't quite, only because I drew that vector, I'm moving there a bit small. Let me just draw it in place. Okay, it ends up looking like this. Okay, so this is, that's the 4 vector there. This one's the P, and that one's the Q. And then what's interesting is you also can kind of find the angles going on in this as well, right? Because here you've effectively got 30 degrees, right? That's 30, isn't it? Because you've been told it's 30 here, and it's the same in this case. So that tells me that the angle inside that triangle here, that's 60 degrees. Okay, and you can use a similar bit of logic to eventually figure out that that's 45 degrees, and then of course this must be 75 degrees here. And what you've now got is you've effectively got a triangle, all angles known, 2 sides are unknown. So you can use your sine rule, right? So you can say 4 over sine 60 equals P over its opposite angle 45 equals Q over sine 75. Okay, and from that you should be able to just figure out what is 4 over sine 60, multiply by sine 45, you'll get P, and then in a separate line of working, multiply this by sine 75, and you'll get Q. Very importantly, this only works, specifically this force triangle method, only works when the object is in equilibrium. So for example, a static particle, because we know the net force is 0, and when the net or resultant force is 0, these 3 forces will make a triangle. They will end where they started, because the total effect is 0. If the resultant force is not 0, then you won't actually get a triangle, you'll get something with a gap. Okay, so that's the second possible method. Both completely valid methods. Try and make sure you understand both, because sometimes one will be the more sensible method, and sometimes the other one will be more sensible. It depends on the particular question you get. Okay, and now talking about this specific kind of problem that we're going to use these rotated axes for. Inclined planes. There's one last example I'll go through, so I won't talk too much on this page, but I just want to make it clear what we're talking about here. When we say static particles on inclined planes, by inclined plane, we literally just mean, we literally just mean a slope. Okay, So inclined plane is just technical terminology for a slope. And it's a slope in the real world in the sense that there's gravity. So you might have a ball, you know, I'm using balls because, you know, they're effectively particles, but really I should be saying a particle. So we've got this particle or a ball on the slope, and it's probably going to roll down the slope, right, or slide down the slope. And you've got various forces acting on it, and problems within inclined plane problems, they ask you to do things like, you know, find out what's happening to this particle in the slope. Does it roll down? Is it going to stay put? Things like this. At this stage, we're talking about static particles. So that means this particular class of problem involves particles sitting on a slope but not moving, right? And you know that can happen. I can place an object on a slope and it doesn't move, and it'll be because there's the correct forces going on that make the net result zero. Things like friction, for example. So you may have the weight of the object pulling it down, but you might have friction preventing it from moving. And of course you've got the normal force of the object itself on the slope pushing back. Okay, but we'll see that in the example. But just to clarify terms here, this is all that inclined planes means. It literally means an object sitting on a slope and there's gravity going on. Okay. Right, so then for this example, this is, let's just clarify what we're looking at in this picture. This object here, this is the ball on our slope. And then you've got 1, 2, 3, 4 forces acting on it. I'm just going to redraw this a bit, just to make it so we can see what's actually going on in terms of the real world. The thing is, they haven't actually told us what any of these forces are. However, from experience, I can certainly say what some of them must be, and likewise you will be able to as well. So this 5 newtons, that's just going to be the weight. Okay, so that's clearly the weight of the object. This 2 newtons, which is perpendicular to the slope or the inclined plane, that's clearly the normal reaction. Okay, so that's the slope pushing up on the ball, preventing it from falling through the surface. That's the normal reaction. The P going up that way, that's going to just be, I don't know. I don't know what that P is. It's probably a typical question like this would say somebody's put a string on the ball and they're pulling the string. I don't particularly know what that P is doing there. It's presumably someone pulling on the ball or something. And the 8 newtons going down the plane, also no idea. We don't know what this force is. It could be, you know, a motor on this object which is force making it go down the plane. Maybe it's a second string also pulling on it. We really don't know. But we don't technically need to know for this question what these forces are. But I do think it helps to give you at least some clue what it might be. Otherwise it just seems like we're working on, you know, random diagrams of random forces and we don't particularly know why. So that's what this situation is probably modelling. An object with some weight, a normal reaction, something's pulling on it this way, and something else is pushing or pulling it down the plane. Okay, right. So now let's actually try and solve the problem. In order to solve this one, let's pick the axes appropriately. And this is the trick with inclined planes. With inclined planes, you should pick the axis so that one line of the axis goes along or parallel to the plane. So this plane here, that green plane, that should be one line of your axes. So I'm going to kind of try and replicate it here. So like that. And then the other line should just be perpendicular to it. Okay. So these should be my axes that I choose. Okay, so these are my chosen axes. And then what that means is I'm going to resolve all my forces with respect to this. Okay, so let's just see it sort of lines up. Oh, it doesn't quite, unfortunately. I didn't quite do that one perpendicular. Let's try that one more time. The reason we do this, remember, because we can choose any axes, so you're thinking, what's the point? Why don't I just stick with the horizontal vertical? The reason we do this is because it will make the calculations much simpler, because many of the forces will just have cancelled out components. Okay, so let's put that there. Right, so let's resolve. Let's see what we can do. In the case of the direction going that way, and let's just make a note here, there's also that direction. Okay, so going up the plane, what forces have we got? Well, we'll have the 8 newtons going down. Okay, that's these -8 here. We will have a component of the 5, right? What are these going to be, actually? That's a good question we need to briefly answer. So this angle here, I'm going to tell you what that is, but you need to think about why. So pause the video if you need a moment. That's 30 degrees. Okay, that's definitely 30 degrees. But you do need to think for a moment how I know that. Okay, obviously it relates to this one here. And what I can now say is this component going down, that's going to be cos 5 cos 30. 5 is the length of the hypotenuse, cos 30 is the cos of the angle, and this one here is 5 sine 30. So now, sorry, going back to here, resolving up the plane, we've got the 8 in that direction. We've got this one, which is 5 sine 30, also going downwards. So that's -5 sine 30. And we've got here, we're going to have to label these as well. Sorry if it's a bit messy. That one there is P times sine 30, and this one over here, that component, that's P, oh sorry, why did I say 30? It's alpha, isn't it? P cos alpha, and let's change that as well, alpha. Okay, and that's for, you know, that component going up that way. So again, going back up the plane, we've got -8, done, -5 sine 30, done, and this one going upwards, that's P cos alpha. Let's add that on, P cos alpha, and that's equal to 0. I didn't need a component for the 2 newtons because there is no component of that which is going in the direction up or down the plane. Okay, and now let's try and do the other direction, the perpendicular to the plane direction. Test, test. So the perpendicular direction, we've got 2 going upwards, so that's a +2. We've got, so you've got to think, remember you've got to check the components of every single force. So the component of the 2 going upwards is the whole thing, is 2. What's the component of the P going perpendicular to the slope? It's this one here. It's P times sine alpha. So that's P sine alpha, and it's going upwards. We've also got, for this 5 Newton force, we've got that component there. That's 5 cos 30, but it's going downwards, so that's -5 cos 30. And what about this 8 newtons force? What component of that is vertical to the plane? None of it, right? It's 0. So it's entirely contained within the axis which is going along the plane. Okay, so that's what I mean when I say we simplify our equations a bit if we do that. So therefore we've got resolving forces up the plane is 0, resolving forces perpendicular to the plane is also 0, and now we can do what we were supposed to do in the first place, which is find what P and alpha are. So in terms of mathematically how are we solving this, we've got two simultaneous equations with two unknowns, which are P and alpha. So now we can sort of get rid of all this, this scaffold of how we got those equations in the first place, and we're just working with simultaneous equations now. Can we solve these to get out our P and our alpha? The way I'd suggest doing that is try and combine the cos alpha and sin alpha. So one way we can do that is to first make them the subjects of their respective equations. So let's say P cos alpha, that's going to be equal to 8 plus 5 sine 30. And P sine alpha is going to be equal to 5 cos 30 minus 2. Now that actually, let's already do it at this stage. 8 plus 5 sine 30, that's 8 plus 5 over 2. Let me just go. I'm getting my calculator out, not for 8 plus 5 over 2, but for the second one as well. And also just maybe to double check. 8 plus 5 over 2, 10.5. Okay, and 5 cos 30 minus 2. I'm just being a bit lazy. We could work this out using surds, but that is minus 4. No, let's write it as a decimal. 2.3301, roughly. Okay. And then if we divide that by this, we're going to get tan alpha, right? Because sine over cos is tan, P over P is 1, so it cancels out. So we get tan alpha on the left, and on the right we're going to get 2.3301 divided by 10.5 equals, and again you could technically have it in surd form, but we're going to just have it as a decimal, 0.22 and round it up to, okay, which in turn can then give you your alpha. Just do tan inverse of 0.222. You get about roughly 12.5 degrees. Okay, that's to one significant figure or something like that. 12.5 degrees for alpha, and you can find your P. Not too difficult. Plug alpha into cos here maybe, and then say 10.5 divided by that. That will give me my P. So you can sort of do that yourself, hopefully, and what we should end up with is a P equal to approximately 10.8. Okay. Also I've just noticed here I said one significant figure is actually one decimal place that I've done there. Okay, and likewise here. Okay, so that's it. We've got alpha, we've got P, and the way we're doing it is by picking an axis which is has one axis parallel to the slope and the other axis perpendicular to the slope. And that doesn't just work for this question. That's how you should do it for all inclined plane problems. Okay, cool. Right, let's have a little bit of practice then. I am going to say there's not that many questions in the sense that there's sort of 3 types of question, I think. However, each of those 3 types has several versions. So for example, this is question 1, has 4 versions. I'm conscious that I've spoken a lot, so you don't have to do everything, but you need to do it enough so that it works and that you understand it. So if you don't quite understand it, then yes, you do need to do them all to make sure you've got the practice in. And don't just obviously look at it and say, I've understood it, I'm not going to do any. You need to do at least have tried some, because you never know where you're going to get caught out, or where you think you maybe know it better than you actually do. So have a go at this question, and you can pause the video now. Okay, and let's take a look at the answer. So there they are. You've got your final values in there. You've got your resolved forces. Okay, question type 2. This is getting you to think about the triangle of forces diagram. Remember, that's when you put the 3 forces. In the specific case, we've got 3 forces on an object. You put the 3 forces head to tail, so they make a triangle. You can only do that when the particles are in equilibrium. Okay, in this case it's static equilibrium, which is fine. Yeah, so give that a go, use a bit of trig, see if you can find the missing forces, magnitudes or angles. Pause the video now. Okay, and your answers are there. And you've got your nice force triangles as well. Okay, and then finally, some inclined plane problems. So try applying what we've just talked about to these inclined plane problems. Can you find the missing forces? Pause the video now. Okay, and the answers are there. Okay, and if you want to, and I promise it's actually not that hard of a challenge. If you want to, you should just do it. Really, go on, have a go. It's the 3 forces general case. So in general, I've got 3 forces of some size, and they make some kind of angle in the following arrangement. Can you show the following? And of course, you can already spot this is in fact the sine rule. You're allowed to assume the sine rule. But can you in detail show how do I get from this to this? I'd suggest drawing the force triangle, which is effectively the proof for this one. Okay, you can give that a go. Pause the video now. And there is the logic. Okay, you can't just jump necessarily straight from one to the other. You do have to have drawn this, and I'm not just talking in terms of exam technique. I'm talking in terms of convincing someone that it's true. This is your force diagram. These are the angles with the 180 in them, and then of course you can use the fact that sine of 180 minus x is the same as sine of x. So you can convert from that back to this. Cool. All right. I'll leave you guys there. Hopefully that's given you plenty to think about and work on.